We're next going to look at rotational kinetic energy. So we already dealt with translational kinetic energy, the energy of motion. When an object moves, that motion has energy associated with it. For translational motion, the kinetic energy was equal to 1/2 of the mass of the object times the speed of that object squared. So think of a basketball that's not rotating, just someone throwing it straight or throwing it a free throw. That projectile has kinetic energy as that basketball moves through that arc. We've only treated objects up to this point as non-rotating objects with reference to their kinetic energy. But objects can rotate. Again, think of that basketball, but now that basketball has spin on it. Or an object sliding down an incline, rather than a block sliding down an incline, now you have a cylinder rolling down an incline. So you can add rotational motion to the motion of an object. Well, we've learned up to this point that the rotational analog of the linear equations, you simply replace the linear component with the with the rotational equivalent. So the translational component is mass, the rotational component is moment of inertia. Right? The moment of inertia is the inertial resistance to the change in rotational motion. Speed squared, this is the linear speed squared, so here we have the angular speed squared. So the rotational kinetic energy equation is 1/2 I omega squared. And again, I comes from the distribution of mass around the axis of rotation. So a ring, a hula hoop rolling down a hill, will have a different result than a solid disc rolling down a hill, than a ball rolling down a hill, a hollow ball rolling down a hill versus a solid ball rolling down a hill. So those you can look up, the I's, you can look up on the table or in your textbook. And then here's the rotation speed. But this equation here is simply for objects with only rotational motion. So a merry-go-round or a bicycle wheel where the bicycle is suspended and the wheel is just spinning. But for a lot of this rotational motion, sometimes there's translational motion as well. My basketball example. When you throw a free throw, right, the ball might spin, but it also moves in the X, Y, and Z direction, or X and Y direction for the case of projectile motion. So if you have translational motion, if the center of mass of the object, if the object basically is moving in the X, Y, or Z direction, then you have to look at the translational kinetic energy of that object. If that object is rotating, then you need to look at the rotational kinetic energy of that object. If the object is rolling or moving translationally and rotating, you have to combine these two. So the total kinetic energy of an object is dependent upon the linear or translational kinetic energy and the rotational kinetic energy. So for an object like a cylinder rolling down an inclined plane, gravitational potential energy of the cylinder at the top is turning into kinetic energy as it rolls down. But you get a different result if you have an object rolling down versus an object sliding down a frictionless surface. An object sliding down a frictionless surface, all of the potential energy goes into translational kinetic energy. The object slides fast. When an object has to roll, some of that gravitational potential energy goes into the linear motion, but some of it goes into the rotation as well. The more energy that goes into rotation, the less energy you have for translation, which means that objects with a high moment of inertia will actually go more slowly down the hill than objects with a low moment of inertia. So if you have a disc versus a hula hoop, let's say they have the same radius, they have the same mass, and you roll them down a hill, the hula hoop with a larger moment of inertia will actually go down the hill more slowly than the disc, which has a lower moment of inertia. Or a sphere, which is only 2/5 mr squared, if it's the same radius, will go down the fastest of the three.